Welcome to the Late Lab. It's lovely to have you here tonight. Before settling into the strange little passageways of quantum reality, where are you watching from? Maybe a darkened room, a quiet sofa, a late-night desk, or somewhere with a blanket pulled slightly too high and a drink slowly going cold nearby. Wherever you are, I hope the room feels peaceful, the day is beginning to loosen, and your mind has just enough space to wander gently. If you enjoy these calm journeys through science, matter, space, time, and all the odd little rules the universe keeps hidden beneath ordinary life, a like and subscribe helps the Late Lab keep glowing away in the background. And if you're already subscribed, thank you, truly. It means a great deal, and it helps this sleepy little corner of science continue drifting along. Tonight the subject is quantum tunneling, one of those ideas that sounds as though physics briefly lost a bet. In the ordinary world, walls are fairly committed to being walls. If you walk into one, the wall does not usually reconsider its position. It simply remains there, with a confidence that can feel slightly rude. But in the quantum world, particles are not quite like tiny marbles rolling neatly through space. They are described by wave functions, probabilities, and energy barriers. And under the right conditions, a particle can appear on the other side of a barrier it should not classically be able to cross. So let's begin, shall we? Can particles really walk through walls, or is quantum tunneling revealing something much deeper about how reality works, when nobody's looking too closely? Imagine just for a moment, a single particle approaching a barrier. Not a dramatic barrier, not a castle wall covered in moss, not a locked iron door in some gloomy corridor, but a barrier in the language of physics, a region the particle should not be able to cross. On one side, the particle exists with a certain amount of energy. On the other side, there is a place it could be found. Between the two sites the problem, the wall, the obstacle, the little stretch of reality that, according to ordinary expectations, should simply say no. In the world of everyday objects, that would be the end of the story. A tennis ball rolling toward a hill either has enough energy to climb over the top or it does not. If it has enough speed, it reaches the crest and rolls down the other side. If it does not, it slows, pauses for a rather humiliating instant, and rolls back down from where it came. Nothing mysterious happens. The ball does not vanish halfway up the hill and appear beyond it, looking quietly pleased with itself. It obeys the rules that large objects usually obey. A locked door works in the same familiar way. If a person has the key, or enough force, or perhaps a worrying commitment to bad decisions, the door may open. If not, the door remains a door. It does not become an invitation. It does not blur into possibility. It just stands there, very pleased with its own solidity. This is the kind of reality human beings are used to. Barriers divide places, obstacles block motion. Walls are objects with boundaries, and those boundaries matter. This ordinary way of thinking belongs to classical mechanics, the older and extremely successful framework of physics, associated above all with Isaac Newton. In classical mechanics, an object has a definite position, a definite speed, and a definite path through space. If the forces acting on it are known, its motion can often be predicted with remarkable accuracy. Newton's laws made sense of falling apples, swinging pendulums, cannonballs, tides, and the motion of planets. They gave the universe a kind of grand clockwork order, where objects moved through space according to rules that were clear, powerful, and beautifully practical. For the world of everyday experience, classical mechanics is still astonishingly good. It explains why a dropped mug falls toward the floor, usually with tragic accuracy. It explains why a car needs fuel to climb a hill, why a thrown stone follows a curved path, and why walking directly into a wall is not a recommended method of entering the next room. Large objects behave as though they occupy clear locations and follow continuous paths. They do not normally appear on the far side of barriers without crossing the space in between, and yet, deep beneath this familiar world, matter does not always behave like a collection of tiny hard beads following tiny invisible roads. At the scale of atoms and subatomic particles, reality is described by quantum mechanics. Here, the rules become less familiar, though not less precise. A particle such as an electron is not described merely as a small dot, with a perfectly known position and speed. It is described by a wave function, a mathematical object that tells physicists about the probabilities of different possible outcomes. This is where the impossible wall begins to soften. Quantum tunneling is the process in which a particle has some probability of being detected on the far side of a barrier that it does not have enough energy to cross according to classical physics. That sentence can sound almost mischievous, as if the particle has discovered a secret side entrance. But the particle is not thinking. It is not choosing. It is not sneaking, cheating, or tiptoeing through forbidden territory with a tiny suitcase. The language of walking through walls is useful because it gives the imagination something to hold on to, but it is not literal. A particle does not walk through a wall like a ghost in a story. Instead, quantum theory says that the particle's wave function can extend into the barrier and, under the right conditions, continue beyond it. If the barrier is thin enough and the particle is light enough, there may be a measurable probability that the particle will be found on the other side. Not a guarantee, not a miracle, a probability. That difference matters. Quantum mechanics does not say that anything can happen in a loose magical sense. It gives very specific predictions about what can happen and how likely those outcomes are. Most of the time, those probabilities are tiny. Sometimes they're so tiny that for all practical purposes they may as well be zero. But in the microscopic world, with particles such as electrons, protons, or alpha particles, the probabilities can become large enough to matter. In fact, they can become large enough to shape stars, radioactive decay, electronics, microscopes, and the structure of modern technology. This is why quantum tunneling is not just a strange party trick tucked away in a textbook. It is one of the clearest reminders that the universe is not built only from the rules that feel natural to human senses. Human intuition was shaped by large objects, warm rooms, solid ground, moving bodies, and things that generally stay where they are put unless a cat becomes involved. But atoms and particles live in a different regime. They are not vague or lawless. They are governed by rules that are deeply consistent, mathematically exact, and repeatedly confirmed by experiment. They are simply not the rules that everyday life trains the mind to expect. The important point is that quantum tunneling does not mean ordinary objects can casually pass through ordinary walls. A person is made of an enormous number of atoms, all interacting with one another, with the air, with light, with heat, and with the wall itself. For a whole person to tunnel through a wall, all of those particles would need to behave in a fantastically coordinated quantum way across a barrier that is enormous compared with atomic distances. The probability is so small that it is not merely unlikely in the way rain is unlikely on a particular afternoon. It is effectively impossible on any meaningful human timescale. The wall may relax. You may relax. The wall is staying where it is. But for a single particle facing a tiny barrier, the story is different. The barrier does not always act as an absolute stop sign. It can behave more like a region where the probability fades but does not instantly vanish. And if that fading probability still reaches the far side, then there is a chance, sometimes a very useful chance, that the particle appears beyond the obstacle. This is the central tension that makes quantum tunneling so fascinating. It is not magic, but it feels magical when viewed through classical expectations. It does not break physics, but it does break the simple assumption that a barrier must either fully block something or fully allow it through. In the quantum world, nature often works with probabilities rather than certainties, and a wall can become less like an absolute boundary and more like a question with a very small but measurable chance of an unexpected answer. So when the question is asked, can particles walk through walls, the calmest answer is that particles do not walk, and walls are not always walls in the ordinary sense. What really happens is stranger and more precise. A quantum particle can have a real probability of being found beyond a barrier that classical physics says it should not cross. That is tunneling. Not a loophole in reality, but part of reality's deeper rulebook. A quiet, measurable shortcut through what once looked impossible. The reason tunneling feels so strange is that the ordinary world teaches a very simple lesson about barriers. If something does not have enough energy to cross an obstacle, it does not cross. It stops, turns back, gets stuck, or waits for help. This is not only common sense. For large objects moving at everyday speeds, it is also excellent physics. In classical physics, a barrier is usually an energy problem. An object needs enough kinetic energy, the energy of motion, to overcome a potential energy barrier. Potential energy is stored energy connected to position or arrangement. A stone held above the ground has gravitational potential energy because of its height. A drawn bow has stored energy because of its shape. A charged particle near another charged particle can have electric potential energy because of the electromagnetic force between them. In each case, the arrangement of things matters, and changing that arrangement requires energy. A gentle example is a ball rolling toward a hill. If the ball is moving quickly enough, it climbs upward, losing kinetic energy as it gains gravitational potential energy. If it reaches the top, it can roll down the other side. But if it is too slow, it rises partway, loses speed, pauses, and then rolls back. There is no secret route through the hill. There is no polite little exemption from the rules. The ball either has enough energy to reach the top, or it does not. Classical physics is very firm about this, rather like a doorman with a clipboard and no interest in hearing excuses. This way of thinking became powerful through the work of Isaac Newton. Newton's laws of motion describe how objects respond to forces, how motion changes, and how action and reaction are related. Combined with his law of universal gravitation, they gave physicists an extraordinary way to understand planets, falling bodies, pendulums, tides, projectiles, and machines. A planet follows a predictable path around the sun. A cannonball curves through the air, a gear turns because another gear pushes it. A bridge holds or fails depending on forces, weights, and materials. Classical mechanics made nature look, in many ways, like an immense clockwork system. For the world that human beings can touch, lift, throw, build, and repair, this picture works beautifully. It explains why a bicycle rolls downhill more easily than uphill, why a car needs power to climb a slope, and why a person cannot stroll through a locked door simply by maintaining a positive attitude. The door is a physical barrier. The person does not have a path through it. Unless the door opens, breaks, or was secretly made of cardboard by someone with a poor sense of architecture, the person remains on the same side. So when classical physics looks at tunneling, it sees a problem that should have only one answer. Imagine a particle approaching an energy barrier. In the classical picture, the particle has a definite position, a definite speed, and a definite amount of kinetic energy. The barrier has a definite height in energy terms. If the particle's energy is greater than the barrier, it can cross. If the particle's energy is lower than the barrier, it cannot. That should be the end of it. This is why quantum tunneling seems impossible from a classical point of view. It is not merely surprising. It appears to violate the whole logic of motion through barriers. A classical particle cannot appear on the far side of an obstacle unless it travelled through the space between and had enough energy to do so. The path must make sense. The energy must add up. The object must go from here to there in a continuous way. But classical physics was built from the behaviour of large objects, not from the behaviour of atoms, electrons, nuclei, and other microscopic systems. It was tested first against falling stones, moving planets, swinging pendulums, and flowing tides. It did not arise from watching individual electrons near tiny barriers only a few atoms wide. That matters, because the microscopic world does not always behave as though it is made of little solid balls following neat invisible tracks. This does not mean classical physics is simply wrong. That would be far too blunt, and also rather unfair to a framework that can send spacecraft across the solar system and predict eclipses with wonderful precision. Classical mechanics is an accurate approximation under many ordinary conditions. It remains one of the great achievements of science. But it is incomplete. At very small scales, where particles have wave-like properties and measurement becomes part of the story, the classical picture no longer gives the full answer. The difficulty comes from one of classical physics' deepest assumptions. It treats a particle as something with a definite path. At every moment, the particle is somewhere. It is moving in some direction. It has enough energy for a journey or it does not. In that world, tunneling cannot happen because there is no allowed route through the barrier. The particle cannot climb over and it cannot pass through, so classical reasoning says it must be reflected back. Yet experiments show that microscopic particles do sometimes appear beyond barriers they should not classically cross. The old picture has reached its limit. To understand what is happening, physicists had to stop asking only where the particle is and how fast it is moving. They had to ask a stranger question. What is a particle, really, when the ordinary idea of a tiny object following a single path no longer works? That question opens the door to quantum mechanics, where particles are described not only by position and motion, but by wave functions, probabilities and possibilities that can fade through a barrier without vanishing at its edge. Classical physics says no, because in its world the barrier is absolute. Quantum physics answers more quietly. It says the wall may still be real, but reality itself is not always as sharply divided as it first appears. Classical physics had done something remarkable. It had made the universe feel understandable. Planets followed paths that could be calculated. Falling objects obeyed patterns. Machines could be built, repaired, improved, and predicted. Light seemed to travel as a wave. Heat could be described through motion, energy, and temperature. By the late 19th century, it was tempting to imagine that physics was almost complete, with only a few small details left to tidy up, like dusting the corners of an already magnificent library. Unfortunately for that comfortable idea, the universe had left a few rather awkward books open on the table. The problems appeared in places that seemed simple at first. One of them came from heat and light. A hot object glows. Warm metal turns red, then orange, then almost white as its temperature rises. This is familiar enough from a blacksmith's furnace, a toaster filament, or the kind of pan that has been left on the hob far too long and is now making its feelings known. Physicists wanted to understand this glow precisely. They studied what was called black-body radiation, the idealized radiation emitted by an object that absorbs and emits light perfectly. Classical theory could describe some of the pattern, but not all of it. At shorter wavelengths, the predictions went badly wrong. The theory suggested that a hot object should emit far too much energy in the ultraviolet range, a failure later nicknamed the ultraviolet catastrophe. It was not a small rounding error. It was nature calmly refusing to follow the instructions classical physics had written for it. In 1900, Max Planck found a way to solve the problem. He proposed that the energy exchange between matter and radiation did not vary in a perfectly smooth, continuous way. Instead, it seemed to come in discrete amounts. These little packets of energy were linked to the frequency of the radiation. Planck did not begin by trying to overturn reality or invent a strange new philosophy. He was trying to make the mathematics match the experiment. The result, however, was revolutionary. Energy, at least in this setting, behaved as though it could be divided into definite steps. That was the beginning of the quantum idea. The word quantum refers to a discrete amount, a portion, a measured packet. It is not mystical language, even though it has been made to wear a great many suspicious hats in popular culture. It began as a practical response to a physical problem. The old theory said energy should behave continuously. The experiment said otherwise. A few years later, Albert Einstein pushed the idea further. In 1905, he examined the photoelectric effect, where light striking a metal surface can knock electrons out of it. Classical wave theory suggested that brighter light should eventually provide enough energy to eject electrons, no matter the colour of the light, if one simply waited long enough. But that was not what experiments showed. Below a certain frequency, no electrons were emitted, even when the light was made brighter. Above that frequency, electrons could be released almost immediately. Einstein explained this by treating light as if it arrived in packets of energy, later called photons. The energy of each packet depended on the light's frequency. If an individual packet did not carry enough energy to release an electron from the metal, then making the beam brighter only added more insufficient packets. It was like trying to unlock a door with 1,000 copies of the wrong key. Admirable enthusiasm, poor result. The photoelectric effect showed that light, which had long been understood as a wave, could also behave like a stream of particles. This did not erase the wave nature of light. It deepened the puzzle. Light was not fitting cleanly into either familiar category. It could behave like a wave in some experiments and like particles in others. The universe had begun to look less like a tidy machine, and more like a very precise machine with an instruction manual written in a language nobody had fully learned yet. Atoms created another problem. According to classical electromagnetic theory, electrons moving around a nucleus should radiate energy and spiral inward. Ordinary matter should not be stable. Atoms should collapse. Since tables, planets, people, and mildly judgmental walls clearly exist, something was missing. Niels Bohr offered an important step in 1913 with his model of the atom. In Bohr's picture, electrons could occupy only certain allowed energy levels around the nucleus. They did not simply drift through any possible orbit. They existed in quantist states, and they could jump between those states by absorbing or emitting definite amounts of energy. This helped explain the spectral lines of hydrogen, the specific colours of light emitted or absorbed by hydrogen atoms. Bohr's model was not the final version of quantum mechanics. Later developments would replace its neat little orbits with a deeper description based on wave functions and probability. But it was a crucial stepping stone. It showed that atoms could not be understood as miniature solar systems, with electrons circling the nucleus like tiny planets. The microscopic world was not just a smaller copy of the familiar one. These discoveries matter because quantum tunneling was not an isolated oddity that appeared from nowhere. It belonged to a much wider crisis in physics. Black body radiation showed that energy exchange could be discrete. The photoelectric effect showed that light could act as though it arrived in packets. Atomic spectra showed that electrons occupied specific energy levels rather than any value they pleased. Again and again, nature behaved in ways that classical physics could not explain by treating matter and light as smooth, continuous, predictable things. This is the world in which tunneling begins to make sense. Not common sense, exactly. Common sense is still standing nearby, looking concerned and holding a clipboard, but scientific sense. At microscopic scales, particles and energy were already refusing to behave like simple little objects moving along simple little tracks. They were obeying rules, but the rules were stranger, deeper, and more exact than the ones built from ordinary experience. Quantum tunneling is one result of that shift. If energy can be quantized, if light can behave like particles, if electrons can occupy allowed states, and if microscopic objects cannot always be described by definite classical paths, then a barrier is no longer quite the simple thing it seemed to be. The wall has not vanished, the obstacle still matters, but the particle approaching it must be described by quantum mechanics, not by the older picture of a tiny hard bead rolling toward a hill. The birth of the quantum problem was therefore not a rejection of reason. It was reason following experiment into uncomfortable territory. Physics did not choose strangeness because strangeness sounded exciting. It accepted strangeness because the evidence kept leading there, softly but firmly, one impossible result at a time. By the early years of quantum theory, light had already begun to behave in a way that made the old categories feel uncomfortably narrow. In some experiments, light spread and interfered like a wave. In others, it arrived in packets, as though it were made of particles. This was strange enough on its own. But then came an even more unsettling possibility. Perhaps matter itself, the stuff that seemed solid, local and particle-like, also carried something wave-like within its description. In 1924, Louis de Broglie proposed that particles such as electrons should be associated with waves. This was a remarkable idea, because electrons had normally been imagined as bits of matter rather than ripples of possibility. De Broglie suggested that a moving particle had a wavelength connected to its momentum. The faster and heavier the particle, the shorter the associated wavelength. For large everyday objects, the wavelength becomes so unimaginably tiny that it has no visible effect. A rolling football does not spread around a room like a wave, which is a mercy for both sport and furniture. But for tiny particles such as electrons, the wavelength can be large enough to matter. This idea became known as the de Broglie wavelength. It did not mean that an electron was secretly a little ocean wave, sloshing through space with foam on top. It meant that the electron could not be fully described as a miniature hard bead with a perfectly definite track. Its behaviour had to include wave-like properties. It could spread, it could interfere, it could produce patterns that only make sense when a quantum state is treated as something more subtle than a tiny object flying along a single invisible line. That may sound abstract, but physics is not built on elegant strangeness alone. It asks nature to answer back. In 1927, Clinton Davison and Lester Germer performed an experiment that gave strong evidence for electron wave behaviour. At Bell Telephone Laboratories, they fired electrons at a crystal of nickel and studied how the electrons scattered. The pattern they observed was not what would be expected from simple little particles bouncing randomly from a surface. It looked like diffraction, the kind of pattern associated with waves encountering a regular structure. Diffraction happens when waves spread and overlap after interacting with an opening, edge, or repeating arrangement. Light can diffract, water waves can diffract, sound can diffract. The Davison-Germer experiment showed that electrons could also produce diffraction patterns under the right conditions. This was powerful evidence that matter really did have wave-like properties. It was not just a poetic suggestion, it was measurable. This changed the meaning of a particle in a very deep way. An electron could still be detected as a localized event, as if it arrived at one place. But before that detection, its behaviour had to be described through a quantum state capable of spreading and interfering. It was not simply following one definite classical path like a pebble tossed through the air. It was governed by a probability pattern, and that pattern could behave in ways that ordinary particles never would. This is where tunnelling begins to feel a little less like a miracle and a little more like a consequence. Classical physics imagines a particle meeting a barrier as though it were a tiny ball hitting a wall. It either has enough energy to cross the obstacle or it does not. But if matter has wave-like properties, then the situation changes. Waves do not always stop with perfect sharpness at a boundary. Their influence can extend into regions where a simple object would appear to be blocked. A gentle comparison is the way sound can be heard faintly through a wall. Someone speaking in another room may be muffled, softened, and blurred, but the sound does not always vanish completely at the boundary. It reaches the wall, interacts with it, and some vibration can carry through. This is not the same thing as quantum tunnelling, and it is important not to confuse the two. Sound travels through physical vibrations in air and solid material. Quantum tunnelling is not a little noise squeezing through a brick. But the analogy helps with one limited idea. A wave can fade across a barrier rather than simply stopping dead at the surface. In quantum mechanics, the relevant wave is not a sound wave or a water wave. It is the wave function, the mathematical description of the particle's quantum state. When a particle meets an energy barrier, its wave function may extend into the barrier instead of ending abruptly. If the barrier is thin enough, the the wave function can still have a small presence on the far side. That presence is linked to the probability of detecting the particle beyond the barrier. This does not mean the particle drills a tunnel, melts the wall, or finds a secret passage. It means the classical picture of collision is no longer enough. The barrier is not being approached by a tiny solid object with a single definite path. It is being approached by a quantum state whose behavior is governed by wave equations and probability. The wall is still real. The barrier still matters. But the sharp certainty of the old picture has softened into a question of likelihood. The discovery that matter behaves like waves was therefore one of the great steps toward understanding tunneling. It showed that particles could not be treated merely as little pellets moving through empty space. They could produce interference, diffraction, and probability patterns. Their behavior depended not only on where they were found, but on how their quantum states spread before measurement. Once matter becomes wave-like, the impossible wall is no longer quite as simple. It is still an obstacle, but not always an absolute ending. At microscopic scales, a barrier can become a place where probability fades, thins, and sometimes reaches beyond. And from that quiet extension of a quantum wave, the strange shortcut of tunneling begins to emerge. The strange thing about quantum tunneling is that it does not really begin with the wall. It begins with the way quantum physics describes the thing approaching the wall. In ordinary life, this sounds like an unnecessary complication. A ball is a ball. A stone is a stone. A sleepy person attempting to find the bathroom in the dark is, with luck, still mostly a person. Large objects seem to exist in one place at a time, with clear edges and fairly dependable habits. They move through space along paths that can usually be imagined, even if nobody calculates them precisely. But at the scale of electrons, atoms, and nuclei, the description changes. The particle is no longer treated simply as a tiny solid object, with a perfectly definite route. In 1926, Erwin Schrödinger introduced the Schrödinger equation, one of the central tools of quantum mechanics. It describes how a quantum state changes over time. In simple terms, it gives physicists a way to calculate how the possibilities associated with a particle evolve. The key object in this description is the wave function. The wave function is not a little glowing cloud of matter floating through space. It is not the particle smeared out like butter on toast, which would be both scientifically misleading and a mildly troubling breakfast image. The wave function is a mathematical description of a quantum system. It contains information about the possible results that could be found when a measurement is made. This matters because quantum mechanics does not usually begin by saying, here is the particle, here is its exact path, and here is precisely where it will go next. Instead, it describes a range of possible outcomes, each with a probability. The wave function is the thing that allows those probabilities to be calculated. It is not vague guesswork. It is not a decorative fog placed over ignorance. It is part of the formal structure of one of the most successful scientific theories ever developed. Max Born gave this idea its crucial interpretation. Born argued that the wave function should be understood in terms of probability. More precisely, the size of the wave function in a particular region is connected to the probability of finding the particle there when it is measured. This was a major shift. It meant that quantum theory was not simply failing to provide a hidden classical path. It was offering a different kind of description, one where probability is built into the way physical systems behave. That can feel unsettling, because probability in everyday life often means incomplete knowledge. If someone says there is a chance of rain, it usually means the atmosphere is complicated and the forecast has limits. The rain itself is not waiting in a philosophical state of indecision. With quantum mechanics, the role of probability is deeper. It is not merely that physicists do not know the exact ordinary path of the electron. The theory itself describes the electron through a wave function, and experiments show that this probabilistic description works with extraordinary accuracy. This is where the idea of a probability cloud can be helpful, as long as it is handled carefully. Around an atom, an electron is often described as occupying a probability cloud. That does not mean the electron has been physically stretched into a mist. It means there are regions where the electron is more likely to be found and regions where it is less likely to be found. The cloud is a map of likelihood, not a blurry photograph of a tiny object. Tunneling becomes possible because the wave function does not always stop sharply at the edge of a barrier. In classical physics, a particle without enough energy reaches the forbidden region and is turned back. The story ends at the wall. But in quantum mechanics, the wave function can extend into the barrier. Usually it becomes smaller as it does so, meaning the probability fades. Yet if the barrier is thin enough, the wave function can still have a small but non-zero presence on the far side. That small presence is the crucial detail. If the wave function reaches beyond the barrier, then there is some probability that the particle will be detected there. Not because it smashed through the wall like a tiny cannonball, not because it found a hidden corridor, not because it briefly became magic and hoped nobody would check the paperwork. It appears beyond the barrier because the quantum state allowed a measurable chance of that outcome. This is why the phrase "walking through walls" is useful but imperfect. A particle does not walk. It does not choose a route. It does not stroll up to a barrier, sigh dramatically, and continue through it out of sheer confidence. The phrase is a human image for something more precise. The particle is described by a wave function, and that wave function can reach into a classically forbidden region. If the conditions are right, the particle may later be measured on the other side. The wall, then, is not ignored. It still affects the particle strongly. A thicker barrier makes tunneling much less likely. A higher energy barrier also makes tunneling much less likely. The obstacle remains real. But it is not an absolute divider in the simple classical sense. In the quantum world, a barrier can reduce probability without completely eliminating it. This is the quiet heart of quantum tunneling. Reality at small scales is not made of tiny solid objects following perfectly visible tracks. It is described by quantum states, probability patterns, and wave functions that can fade where classical motion is forbidden. What looks like a particle walking through a wall is really the deeper mathematics of possibility reaching just far enough beyond the barrier for nature to occasionally answer yes. A barrier in quantum physics is not always the kind of wall that can be touched, painted, knocked on, or blamed when someone walks into it at night. Often, it is not a wall in the ordinary sense at all. It is a region of energy. More precisely, it is a region where a particle has less energy than the potential energy associated with that region. In classical physics, that makes the region forbidden. The particle should not be able to enter it, cross it, or appear beyond it, because it simply does not have enough energy to be there. This is where the language can become slightly slippery. When the word barrier is used in everyday life, it usually means something solid. A fence, a locked gate, a brick wall, a closed door, or the tragically immovable side of a cupboard discovered by a sleepy toe. But in quantum tunneling, the barrier is usually better understood as an energy obstacle. It may be created by electric forces, nuclear forces, or the structure of a material. The particle is not necessarily facing a physical wall. It is facing a region where, according to classical reasoning, its energy is too low for that region to be accessible. Potential energy is the key idea here. In a gravitational field, an object higher up has more gravitational potential energy than an object lower down. A ball rolling toward a hill must convert kinetic energy, the energy of motion, into gravitational potential energy as it climbs. If it does not have enough kinetic energy to reach the top, it stops and rolls back. That is the familiar picture. It is clear, tidy, and extremely good for hills, balls, ramps, cars, and other things that do not usually require a full quantum description before breakfast. In the microscopic world, potential energy can come from different sources. An electron approaching a thin insulating layer may face an electric energy barrier, created by the arrangement of charges in the material. An alpha particle inside an atomic nucleus may face a barrier connected to the electric repulsion between its positive charge and the positive charge of the remaining nucleus. Protons in the core of a star repel one another because they both carry positive electric charge, creating a barrier that must somehow be overcome before the strong nuclear force can bind them together. In each case, the barrier is not simply a lump of matter in the way a brick wall is. It is a landscape of energy. Classical physics treats that energy landscape in a very strict way. If a particle does not have enough energy to occupy a region, it cannot go there. This is the classically forbidden region. The phrase sounds almost dramatic, as if the particle has reached a velvet rope outside a very exclusive nightclub. But the meaning is precise. In Newtonian reasoning, the particle's motion must remain consistent with its energy. If entering a region would require more energy than the particle has, then the particle is excluded from that region. It must be reflected back or remain trapped on its original side. That picture works beautifully for large objects. Isaac Newton's laws of motion describe how objects respond to forces, and in ordinary conditions they give a deeply reliable account of motion. A thrown stone, a swinging pendulum, a falling apple, or a planet moving around the sun can be understood through forces, energy, and trajectories. In that world, there is no need for an object to have a faint probability of existing where it does not have enough energy to be. It either can go there, or it cannot. Quantum mechanics changes the story because a particle is not described only as a tiny object with a definite path. It is described by a wave function. When a quantum particle meets a barrier, the wave function does not usually stop instantly at the boundary. Instead, inside the barrier it tends to decay. That means it becomes smaller as it extends through the forbidden region. The probability linked to the particle fades, often very quickly, but it does not necessarily vanish at once. This fading is the central reason tunneling can happen. If the barrier is not too wide, the wave function may still have a small presence on the far side. And if there is a small presence on the far side, then there is a small probability that the particle will be detected there. The particle has not climbed over the barrier in the classical sense. It has not smashed through it. It has not borrowed a hard hat and started quietly excavating. Rather, the wave function has extended through a region where classical motion would be forbidden, and the quantum rules allow a chance of transmission. Two features matter especially: barrier height and barrier width. Barrier height means how much potential energy the barrier represents compared with the particle's energy. A higher barrier makes tunneling less likely. Barrier width means how far the forbidden region extends. A wider barrier also makes tunneling less likely. These two details are crucial because the wave function usually decays very rapidly inside the barrier. A slight increase in width or height can reduce the tunneling probability enormously. This is why tunneling can be important for particles and still irrelevant for people walking into walls. An electron facing a barrier only a few atoms thick may have a meaningful chance of tunneling. An alpha particle inside a nucleus may escape by tunneling because the distances involved are incredibly small. Protons inside stars may sometimes tunnel close enough together for nuclear fusion to occur. In these cases, the barriers are tiny on human scales, and the particles are light enough for their quantum behavior to matter. A brick wall is a very different kind of problem. It is not a neat single barrier faced by one isolated particle. It is an enormous, warm, complicated arrangement of atoms and molecules, all interacting with one another and with the world around them. A person is also an enormous collection of particles, constantly interacting internally and externally. For a person to tunnel through a wall, all the particles making up that person would need to appear on the other side in the right arrangement, while the wall's particles somehow allowed the process in a fantastically coordinated way. The probability is so tiny that calling it unlikely almost feels too generous. It is effectively zero for any practical purpose, so the ordinary wall remains reassuringly wall-like. It will not become passable because quantum mechanics exists. The rules that allow tunneling are real, but they become significant only under particular conditions, usually involving tiny particles, tiny distances, and carefully defined energy barriers. Quantum mechanics does not turn every obstacle into a suggestion. It gives precise probabilities, and most large-scale tunneling probabilities are vanishingly small. This makes quantum barriers both strange and disciplined. They are not magic doors. They are not gaps in reality. They are energy regions where classical physics would forbid a particle from existing, but where quantum mechanics allows the wave function to fade rather than disappear. If that fading presence reaches far enough, a particle may be found beyond the barrier. The wall, then, is not ignored. It still matters deeply. It shapes the probability, weakens the wave function, and often stops the particle completely in practice. But at microscopic scales, the barrier is not always an absolute ending. Sometimes it is a region of fading possibility, and on rare but measurable occasions, possibility reaches the other side. The mathematics of quantum tunneling can look rather intimidating from a distance. There are wave functions, boundary conditions, potential barriers, exponential curves, and symbols that seem to have arrived from a very serious alphabet committee. But the basic shape of the idea is gentler than it first appears. At its heart, tunneling is about how a quantum wave function behaves when the space around it changes. A particle approaching a barrier is not described in quantum mechanics as a tiny bead moving along a single invisible rail. It is described by a wave function, and that wave function changes depending on the region the particle is in. In a region where the particle is classically allowed, meaning it has enough energy to exist there according to ordinary energy rules, the wave function can behave in a wave-like way. It can rise and fall, it can oscillate, it carries the pattern of a quantum state that is allowed to move through that region. That word oscillate simply means to repeat a rising and falling pattern. A swinging pendulum oscillates, a plucked guitar string oscillates, a water wave rises and dips as it travels. The quantum wave function is not the same kind of physical wave as a guitar string or a ripple on a pond, but the repeating pattern helps describe the possible motion of the particle. Where the particle has enough energy to exist in the classical sense, the mathematical description has this wave-like rhythm. Then the wave function reaches the barrier. In classical physics, this is where the particle would be stopped if it did not have enough energy. The story would be clean and decisive. The particle reaches the forbidden region, fails the energy test, and turns back. It is a very tidy answer, which is always pleasant, even when the universe has no intention of being tidy. Quantum mechanics gives a different description. Inside the barrier, where the particle has less energy than the potential energy of that region, the wave function usually does not keep oscillating in the same way. Instead, it begins to decay. This does not mean the particle is rotting away, which would be an unnecessarily dramatic fate for an electron. It means the size of the wave function becomes smaller as it extends into the barrier. The probability connected with the particle fades. The important word is fades. The wave function does not usually slam to zero at the barrier's edge. It does not meet the obstacle and vanish like a candle being pinched out. It decreases as it moves through the classically forbidden region. If the barrier is thick, the wave function may become so tiny by the time it reaches the far side that the chance of detecting the particle beyond it is effectively gone. But if the barrier is thin enough, some of the wave function may still remain beyond the barrier, and that leaves a real probability of finding the particle there. The kind of fading involved is called exponential decay. Exponential decay is a process where something decreases by a repeated proportion rather than by equal steps. A simple way to imagine it is to picture a sound becoming muffled very quickly as more and more material is placed between the source and the listener. The comparison is not exact, because sound moves through physical vibrations while tunneling is a quantum effect. But it gives a useful feeling for the shape of the change. The wave function can shrink rapidly as the barrier becomes wider or harder to cross. This is why small differences matter so much. A barrier that is only a little wider can reduce tunneling probability by an enormous amount. A barrier that is a little higher in energy can do the same. The effect does not usually decline in a slow, gentle, straight line. It can collapse very quickly. This is one reason tunneling can be important for electrons facing barriers only a few atoms thick, while remaining irrelevant for a human body facing a brick wall. The brick wall is not just slightly wider than an atomic barrier. It is unimaginably wider on the scale that matters to an electron's wave function. The Schrödinger equation is the formal tool that predicts this behavior. Introduced by Erwin Schrödinger in 1926, it tells physicists how the wave function of a quantum system changes. When the equation is applied to a particle approaching a barrier, it does not simply ask whether the particle has enough energy in the classical sense. It describes how the wave function behaves on the near side, inside the barrier, and on the far side. The mathematics has to fit smoothly across those regions, and that smooth matching is what allows a small part of the wave function to continue beyond the forbidden zone. This is the quiet mathematical doorway through which tunneling enters. The particle is not borrowing energy in the casual way the idea is sometimes described. It is not sneaking a little energy from the universe and promising to return it later, like a tiny quantum library book. That picture can be tempting, but it is not the cleanest explanation. The better description is that the particle is represented by a quantum state, and the wave function for that state can extend into a region that classical physics would forbid. If the wave function reaches the other side with non-zero size, there is a calculable probability of transmission. Transmission means that the particle is found beyond the barrier. Reflection means that it is found back on the side it came from. Quantum theory can predict the probabilities of these outcomes. It does not say the particle definitely tunnels every time. It does not say the barrier is meaningless. In many cases, reflection is far more likely than transmission. But transmission is not always impossible. That is the strange and measurable point. The uncertainty principle, associated with Werner Heisenberg, belongs to the wider quantum picture and is often mentioned when people try to explain tunneling. It tells us that certain pairs of physical properties such as position and momentum cannot both be known with unlimited precision at the same time. This principle is deeply important, but it should be handled carefully. It does not mean anything can happen simply because the universe is a bit blurry around the edges. It does not mean particles are free to ignore all rules whenever they feel mysterious. Quantum mechanics is not a permission slip for chaos. It is a precise theory with strict mathematical structure. Tunneling is therefore not best understood as a random miracle. It is a consequence of the wave function, the energy barrier, and the way quantum states evolve according to the Schrödinger equation. Where the particle is classically allowed, the wave function can oscillate. Where the particle is classically forbidden, the wave function can decay. If the decay is not complete before the far side of the barrier is reached, tunneling remains possible. That is the mathematics without the migraine. A particle approaches a barrier. The wave function changes shape across the regions. It fades inside the forbidden zone instead of disappearing instantly. The taller and wider the barrier becomes, the faster the possibility shrinks. Yet when the barrier is small enough, and the particle is quantum enough for its wave nature to matter, the probability can survive. What looks from the outside like a particle crossing an impossible wall is, underneath, a carefully described change in a wave function. The impossible shortcut is not a crack in the rules. It is what the rules predict when reality is described at its smallest scales. One of the first places quantum tunneling proved its usefulness was not in a laboratory device, or a futuristic computer, or a neatly arranged thought experiment, but inside the atomic nucleus. There, in a region so small that ordinary imagination has very little to hold on to, physics found one of its strangest escape stories. The process is called alpha decay. In alpha decay, an unstable atomic nucleus emits an alpha particle. An alpha particle is made of 2 protons and 2 neutrons, the same basic structure as the nucleus of a helium atom. Many heavy radioactive elements can release alpha particles as they decay, changing into different elements in the process. This was one of the great puzzles of early nuclear physics, because the particle seemed to escape from a place where classical physics said it should have remained trapped. Ernest Rutherford played a central role in revealing the structure of the atom and the nature of radioactivity. Through his work on alpha particles, radioactive decay, and the atomic nucleus, Rutherford helped transform the atom from a vague unit of matter into a structured system with a tiny, dense, positively charged centre. His gold foil experiment, carried out with Hans Geiger and Ernest Marsden, showed that most of an atom is empty space, while most of its mass and positive charge are concentrated in the nucleus. It was an astonishing discovery. The atom was not a soft little pudding of charge, it had a heart. But that heart raised new questions. Some atomic nuclei were stable, while others decayed. Some released alpha particles quickly, others did so only after enormous lengths of time. The pattern was not easy to explain with classical ideas alone. If an alpha particle was bound inside a nucleus, then why did it ever escape? And if it could escape, why did it not simply do so immediately? Inside the nucleus, the alpha particle is held by the strong nuclear force. This force is enormously powerful over very short distances. It helps bind protons and neutrons together inside atomic nuclei, overcoming the electric repulsion between positively charged protons. But once the alpha particle begins to move away from the nucleus, the situation changes. Outside the range of the strong nuclear force, the alpha particle faces electric repulsion from the remaining positively charged nucleus. This creates an energy barrier. Classically, that barrier should be a serious problem. The alpha particle does not usually have enough energy to climb over it. In the old picture, it should remain trapped inside the nucleus, like a small object inside a deep well, whose walls are too high to climb. If the particle lacks the energy needed to escape, Newtonian reasoning says it should not get out. No shortcut. No mysterious exit. No tiny nuclear trapdoor politely opening at the right moment. Yet alpha decay happens. In 1928, George Gamow applied quantum tunneling to this problem. He showed that the alpha particle did not need to climb over the barrier in the classical sense. Instead, its wave function could extend into and through the barrier, creating a probability that the particle would be found outside the nucleus. Around the same period, Ronald Gurney and Edward Condon independently developed a tunneling explanation for alpha decay. This was a major success for quantum mechanics, because it turned a deep puzzle into a calculable physical process. The alpha particle is not smashing its way out. It is not waiting until it suddenly receives a secret burst of extra energy. It is not picking the lock on the nucleus, though that image does have a certain tiny criminal charm. The better description is that the alpha particle's quantum state has a small chance of extending beyond the nuclear barrier. Most of the time, it remains trapped, but every so often, according to a precise probability, it appears outside. Once outside, the electric repulsion pushes it away, and alpha decay has occurred. This also helps explain half-life. A radioactive half-life is the time it takes for half of a large sample of unstable nuclei to decay. It does not tell exactly when one individual nucleus will decay. Instead, it describes the statistical behavior of many nuclei together. One nucleus may decay very soon, another may remain unchanged for much longer. But across a large number of atoms, the pattern becomes predictable. Quantum tunneling explains why half-lives can vary so dramatically. The chance of tunneling depends very strongly on the height and width of the energy barrier. A small change in the barrier can make the tunneling probability enormously different. Because the probability falls so sharply, two nuclei with somewhat different barriers can have half-lives that differ by many orders of magnitude. One may decay quickly, while another may endure for vast stretches of time. The nucleus is not deciding when to decay. It is obeying a probability rule built into quantum mechanics. Alpha decay shows tunneling at its most elegant and serious. The idea of particles crossing forbidden barriers can sound like a strange classroom puzzle, but inside unstable nuclei it becomes a real physical process. It explains why certain atoms change into other atoms, why radioactive materials release particles, and why the microscopic world cannot be understood as a simple collection of tiny balls trapped behind tiny walls. A barrier still exists. The nucleus still holds the alpha particle strongly. Classical physics still gives a useful picture of the obstacle, but quantum mechanics adds the missing detail. The wall is not always an absolute ending. Sometimes at nuclear scales it is a region where probability becomes very small, but not zero. And from that small probability, an alpha particle can escape the nucleus, carrying with it one of the earliest and clearest signs that the impossible shortcut is not impossible after all. The same quantum shortcut that lets an alpha particle escape from a nucleus also helps explain something far more familiar, far warmer, and usually taken for granted every time morning arrives. It helps explain why the sun shines. At first, that may sound like an enormous leap. Alpha decay belongs to unstable atomic nuclei. Sunlight belongs to blue skies, warm windowsills, green plants, and the slightly heroic feeling of stepping outside after several days of grey weather. But deep inside the sun, far below the glowing surface that can be seen from Earth, the same basic quantum idea matters. Particles face a barrier. Classical physics makes the crossing difficult. Quantum tunneling allows a small probability of success. And when that success happens often enough inside a star, the result is light. Stars shine through nuclear fusion. In fusion, light atomic nuclei combine to form heavier nuclei, and energy is released because the final arrangement is more tightly bound than the starting arrangement. In the Sun, the most important process begins with hydrogen nuclei, which are simply protons. Through a chain of reactions called the proton-proton chain, hydrogen is gradually converted into helium. Along the way, energy is released as light, motion, and tiny particles called neutrinos. This sounds simple when said quickly. Hydrogen becomes helium, energy comes out, the sun glows. Lovely. A neat little stellar recipe, if one ignores the fact that the kitchen is a sphere of plasma more than 1 million kilometers across, and the oven has been running for billions of years. The difficulty is that protons do not naturally like getting close to one another. Each proton carries positive electric charge. Like charges repel through the electromagnetic force, so two protons approaching each other push apart. This repulsion creates an energy barrier. For nuclear fusion to happen, the protons must come extremely close enough for the strong nuclear force to take over. The strong nuclear force is enormously powerful, but only across incredibly tiny distances, roughly the scale of an atomic nucleus. Before that force can bind particles together, the protons have to get past their mutual electric repulsion. In classical physics, this is a serious problem. The core of the Sun is extremely hot, around 15 million degrees Celsius, and the particles there move very quickly. But temperature is not the whole story. Temperature measures the average motion of particles, and even in the solar core, many protons do not have enough energy to simply climb over the electric barrier between them. If classical physics alone were used, the Sun's fusion rate would be much harder to explain. The protons would often approach, repel one another, and fly apart again, like two polite guests at a party who realize too late they are wearing the same magnetic personality. This puzzle was part of a much larger question in astrophysics. In the 19th century, scientists knew that the Sun had to be powered by something, but ordinary chemical burning could not last nearly long enough. A sun powered like a giant coal fire would run out far too quickly compared with the age of Earth and the evidence from geology and biology. Gravitational contraction, where the Sun slowly shrinks and releases energy, helped explain some possibilities, but not the full lifetime of the Sun. Arthur Eddington was one of the key figures who saw that nuclear processes could be the answer. In the early 20th century, he argued that stars could be powered by the conversion of hydrogen into helium, connecting stellar energy to the deep structure of matter itself. Later, Hans Bethe gave a detailed explanation of stellar fusion processes, especially in work from the late 1930s. Bethe showed how nuclear reactions could power stars, including the proton-proton chain that dominates in stars like the Sun and the carbon-nitrogen-oxygen cycle that becomes especially important in more massive stars. Quantum tunneling is crucial because it allows some protons to get close enough for fusion, even when they do not have enough classical energy to overcome the electromagnetic barrier directly. The protons are not simply smashing over the barrier like tiny cannonballs. Their quantum wave functions can extend through the classically forbidden region. Most of the time, nothing happens. The particles approach, repel, and separate. But occasionally the wave function allows the protons to be found close enough together for the strong nuclear force to act. Once the strong nuclear force takes hold, the situation changes dramatically. At very short distances, it can bind nucleons together. In the first step of the proton-proton chain, two protons come close enough that one can transform into a neutron through the weak nuclear interaction, forming deuterium, which is a heavy form of hydrogen. This step is rare because it depends not only on tunneling through the electric barrier, but also on the weak interaction. That rarity matters. It means the Sun does not burn through its fuel all at once. This is one of the most quietly important details in the story. Tunneling helps fusion happen, but it does not make fusion easy. For any single proton in the Sun's core, fusion is still extremely unlikely at any given moment. The core is crowded, hot and dense, yet the process is slow for individual particles. Because there are so many protons in the Sun, even rare events add up to an enormous total output. But because each individual event is rare, the Sun shines steadily over billions of years instead of exploding through its hydrogen in a brief, spectacular tantrum. That balance is part of why life on Earth has had time to develop. The Sun is not a violent flashbulb. It is a long-lived main sequence star, quietly converting hydrogen to helium in its core. Every second, an enormous amount of hydrogen is processed through nuclear reactions, and a small fraction of mass is converted into energy, according to the principle associated with Albert Einstein. Energy equals mass multiplied by the speed of light squared. That energy gradually works its way outward through the Sun, being absorbed and re-emitted countless times before eventually escaping from the surface as sunlight. The light that reaches Earth has therefore had a long and complicated history. It begins in the deep solar core, where quantum tunneling helps protons approach closely enough for nuclear fusion. The energy produced then moves through the Sun's interior, taking a wandering path through dense plasma before finally emerging from the photosphere, the visible surface of the Sun. A little over 8 minutes later, sunlight crosses the distance to Earth. It warms oceans, drives weather, powers photosynthesis, and lights the world in a way that feels completely ordinary until the physics beneath it is considered. This makes quantum tunneling feel less like a strange footnote and more like a hidden participant in everyday life. It is involved in the processes that allow the Sun to shine at its observed rate. Without tunneling, the barrier between protons would be far more difficult to cross under solar conditions. The Sun as it exists would not work in the same way. The gentle daylight falling through a window is connected by a long chain of cause and effect to particles doing something that classical physics would have called impossible. There is a lovely restraint in this. Tunneling does not make the Sun magical, it makes the Sun understandable. The old classical picture could not quite explain how protons overcame their repulsion often enough in the solar core. Quantum mechanics supplied the missing detail. It showed that a barrier does not always need to be climbed over. Sometimes, at very small scales, probability can reach through. So the warmth on your skin, the green of a leaf, the movement of air across a field, and the slow rhythm of life on Earth all trace back in part to a quantum process hidden deep inside a star. The Sun shines because gravity compresses its core, because the temperature is immense, because nuclear forces bind matter, because the weak interaction allows transformations, and because quantum tunneling gives some particles a tiny chance to cross a barrier they could not classically overcome. That tiny chance, repeated across the vastness of the solar core, becomes daylight. After tunneling has appeared inside the atomic nucleus and deep in the solar core, it may feel as though it belongs only to extreme places, radioactive nuclei, stellar interiors, regions of nature where temperatures, forces, and densities are so far from ordinary life that the human imagination has to quietly sit down for a moment. But tunneling is not confined to the centres of atoms or the hearts of stars. It also appears at the edges of matter, in the behaviour of electrons inside materials. An electron in a solid is not best imagined as a tiny planet circling neatly around one atom, minding its own business in a miniature orbit. That picture can be useful at an early stage, but it becomes too simple when many atoms are arranged together in a solid. In a crystal, atoms sit in a regular repeating pattern called a lattice. The electrons in that lattice are influenced not just by one atom, but by the whole repeating structure around them. Their behaviour is governed by quantum states spread through the material. This is where energy bands become important. In an isolated atom, electrons can occupy certain allowed energy levels. In a solid, where enormous numbers of atoms are packed together, those individual levels broaden into bands of allowed energies. Between these bands there can be gaps, called band gaps, where electron states are not allowed. This band structure helps explain why some materials conduct electricity easily, while others resist it. In a conductor, such as copper, electrons have available quantum states that allow them to move through the material readily. In an insulator, such as glass or many ceramics, the relevant energy gap is large enough that electrons cannot easily move into states where they can conduct electricity. A semiconductor sits between these extremes. Materials such as silicon have band gaps that can be controlled by temperature, impurities, and electric fields. This is the quiet quantum foundation beneath modern electronics, where the difference between conducting and not conducting can become a useful switch. Felix Bloch made a major contribution to this understanding with the quantum theory of electrons and crystals. In the late 1920s, Bloch showed how electron wave behaviour could be described in a periodic crystal lattice. The resulting idea, often called Bloch's theorem, became central to solid-state physics. It helped reveal that electrons in a crystal are not simply bouncing from atom to atom like tiny pinballs in a very serious arcade machine. They behave as quantum waves shaped by the repeating pattern of the material. Once electrons are understood this way, tunneling becomes less surprising, though still wonderfully strange. If two conducting materials are separated by a very thin insulating layer, classical physics would say the electron should be blocked. The insulating layer is the wall. The electrons do not have enough energy to pass through it in the ordinary way, but if the barrier is thin enough, the electron wave function can extend through the insulating region and have a small presence on the far side. That gives the electron a real probability of being detected across the barrier. This is electron tunneling. The wall in this case is not a brick wall or a door or a heroic medieval fortress resisting a siege. It may be a layer only a few atoms thick. On human scales, that is barely a whisper of a wall. On quantum scales, it can still be a serious energy barrier. The important point is that the barrier is thin enough for the wave function not to fade away completely before reaching the other side. A useful example is a thin insulating layer between two metals. Electrons in one metal may face an energy barrier created by the insulator. Classically, they should not cross unless they are given enough energy to go over the barrier. Quantum mechanically, some electrons can tunnel through. The probability depends strongly on the barrier's thickness and height. A slightly thicker layer can make the tunneling current drop dramatically, because the wave function decays rapidly inside the forbidden region. Ralph Fowler and Lothar Nordheim described an important form of this process in 1928. Fowler-Nordheim tunneling explains how electrons can be emitted from a material through a surface barrier when a strong electric field is applied. In this situation, the electric field changes the shape of the energy barrier, making it narrow enough for electrons to tunnel out. This kind of field emission became important in understanding electron sources and later technologies that depend on moving electrons with great precision. The essential idea is calm but powerful. A material surface can act like a barrier. An insulating layer can act like a barrier. An electric field can reshape that barrier. And electrons, because they are quantum objects described by wave functions, can sometimes appear where classical physics would not expect them. They are not punching holes in the material. They are not squeezing through cracks in the ordinary mechanical sense. Their quantum state allows a probability of crossing an energy obstacle. This is one of the reasons tunneling became more than an odd theoretical effect. Once physicists and engineers understood it, tunneling could be controlled. It could be measured as a current. It could be used to probe surfaces, design devices, and understand the limits of miniature electronics. The same principle that sounds so dreamlike when described as particles walking through walls becomes practical when the wall is only a few atoms thick and the particle is an electron. At the edge of matter, the impossible shortcut becomes a tool. Electrons do not behave like tiny classical marbles rattling through wires. They occupy quantum states, move through energy bands, respond to material structures, and sometimes tunnel through barriers that would have stopped them in the older picture. The wall is still there, the barrier still matters, but in the quantum world of solids, even the edge of a material is not always an absolute boundary. Sometimes it is a place where probability thins, reaches, and quietly crosses over. Once electrons could be understood as quantum waves moving through the structured world of solids, tunneling stopped being only a strange explanation for natural processes. It became something that could be designed. A barrier could be made thin enough. A material could be arranged carefully enough. A voltage could be applied in just the right way. And suddenly, the impossible shortcut was no longer merely something that happened inside nuclei or stars. It was something engineers could place inside a real electronic device. One of the earliest and clearest examples was the tunnel diode. A diode is a device that usually allows electric current to pass more easily in one direction than the other. Ordinary diodes depend on the behavior of a junction between two differently prepared regions of semiconductor material. A tunnel diode, however, is different because it deliberately uses quantum tunneling as part of its operation. It does not treat tunneling as an awkward leakage problem or a peculiar laboratory curiosity. It makes tunneling the main act. The tunnel diode effect was discovered by Leo Esaki in 1957, while he was studying heavily doped semiconductor junctions. Esaki later shared the Nobel Prize in Physics in 1973 for work connected to tunneling phenomena in semiconductors and superconductors. His discovery showed that quantum tunneling was not only real in principle, but useful in practice. It could shape how electric current flowed through a device small enough to belong inside the growing world of electronics. The key to a tunnel diode is the junction between two heavily doped semiconductor regions. Doping means adding carefully chosen impurities to a semiconductor in order to change the number and type of charge carriers available inside it. In a normal semiconductor device, doping is already important because it controls how easily electrons or missing electron states can move. In a tunnel diode, the doping is especially heavy, which makes the junction between the two regions extremely thin. That thinness matters. In a classical picture, an electron approaching the junction may face an energy barrier that it should not be able to cross. If the electron does not have enough energy to go over the barrier, it should be stopped. But quantum mechanics allows the electron's wave function to extend through the narrow forbidden region. If the barrier is thin enough, there is a significant probability that the electron will appear on the other side. In other words, current can flow because electrons tunnel. This does not mean the electrons are slipping through little cracks in the material. There is no tiny doorway hidden in the semiconductor, no microscopic employee entrance with a small sign saying electrons only. The barrier is an energy barrier created by the structure of the material and the arrangement of allowed electron states. The electrons cross it because their quantum states allow a probability of transmission through a very narrow forbidden region. The tunnel diode is especially famous for a behavior called negative differential resistance. In most simple electrical components, increasing the voltage tends to increase the current. Push harder and more charge flows. That is the ordinary expectation. But in part of a tunnel diode's operation, increasing the voltage can actually cause the current to decrease. This sounds backwards, and in a cheerful everyday sense it is backwards. The device is not broken, it is following quantum rules. The reason has to do with the alignment of available electron states on the two sides of the junction. At certain voltages, electrons have many matching states available across the barrier, so tunneling is strong and current flows readily. As the voltage changes further, those states become less well aligned. Even though the applied voltage has increased, fewer electrons can tunnel into suitable states on the other side, so the current falls. Later, at still higher voltages, ordinary conduction processes can become more important again. This strange dip in current is not just an oddity. Negative differential resistance can be used in electronic circuits, especially for oscillators, amplifiers, and very fast switching under the right conditions. Tunnel diodes can respond extremely quickly because tunneling itself does not depend on the slower movement of charge across a larger region in the same way some other semiconductor processes do. That made them interesting for high-speed electronics, especially in earlier decades when their unusual behavior opened possibilities that ordinary devices did not easily provide. At the same time, it's important not to overstate their role. Tunnel diodes did not become the main engine of all modern electronics. They are specialized components, useful in particular situations rather than everywhere. Much of the electronic world is dominated by transistors, integrated circuits, and many other semiconductor devices. The tunnel diode belongs to a more specific family of tools, but its importance is still deep, because it showed that tunneling could be deliberately engineered into a working device. That changed the meaning of quantum tunneling in a subtle but powerful way. It was no longer just a strange escape from the nucleus, or a hidden process helping the sun shine. It had become a controlled feature of human technology. A carefully prepared material could turn a classically forbidden crossing into a measurable current. A tiny barrier could become useful precisely because electrons did not obey the old picture of solid little particles moving along simple paths. The tunnel diode is therefore a small device with a large lesson inside it. Quantum effects are not merely distant, delicate, or philosophical. Under the right conditions, they can be built into circuits. The impossible shortcut can be shaped, measured, and used. And in that carefully designed junction, only a few atoms thick in the way that matters, the wall becomes less like a final stop and more like a narrow place where probability quietly does its work. One of the most beautiful uses of quantum tunneling is not only that it explains something hidden, but that it allows something hidden to be seen. Not seen in the usual sense, with glass lenses and light bouncing into the eye, but revealed by an instrument so sensitive that the tiny changes at the surface of matter can be mapped atom by atom. This instrument is the scanning tunneling microscope. It is one of those scientific devices whose name tells the truth quite directly, though not very gently. It scans, it uses tunneling, and it is a microscope, though not like the kind found in a school laboratory, where a drop of pond water becomes an entire drifting universe of suspicious little specks. The scanning tunneling microscope was developed in the early 1980s by Gerd Binnig and Heinrich Rohrer at the International Business Machines Research Laboratory in Zurich. Their work was so important that they received the Nobel Prize in Physics in 1986. The instrument opened a new way of studying surfaces, allowing scientists to resolve individual atoms on conducting and semiconducting materials. It turned tunneling from a hidden quantum process into a tool for touching the edge of matter with extraordinary delicacy. The basic idea is wonderfully simple in outline, though very difficult in practice. The microscope uses an extremely sharp conducting tip, often ending in only one or a few atoms. This tip is brought very close to the surface being studied, so close that the gap between them may be less than a nanometer. A nanometer is 1/1000th of a meter, a distance so small that ordinary human comparisons begin to run out of breath. The tip does not scrape across the surface like a tiny needle dragging over a record. Instead, it hovers just above it. a voltage is applied between the tip and the sample. Classically, electrons should not be able to cross the empty gap because there is a barrier between the two conducting regions. But quantum mechanically, the electron wave function can extend across that narrow space. If the tip is close enough, electrons can tunnel between the tip and the surface, creating a tiny current. That current is called the tunneling current, and it is exquisitely sensitive to distance. If the tip moves only a little closer to the surface, the current can increase sharply. If it moves slightly farther away, the current can drop dramatically. This happens because tunneling probability depends very strongly on barrier width. The gap between tip and surface is the barrier, and even a tiny change in that gap makes a large difference to how easily electrons tunnel across it. This sensitivity is what makes the scanning tunneling microscope so powerful. As the tip moves across the surface, the instrument measures the tunneling current. By adjusting the height of the tip to keep that current constant, or by recording how the current changes as the tip scans, scientists can build a map of the surface. Tiny rises and dips in the electronic structure of the material become visible in the data. Individual atoms can appear as features in the resulting image. It is important to say carefully what kind of seeing this is. The scanning tunneling microscope does not take an ordinary photograph of atoms. It does not shine light on them and capture a picture in the way a camera photographs a tree, a face, or a cat sitting exactly where it has been asked not to sit. Atoms are far smaller than the wavelength of visible light, so ordinary optical imaging cannot resolve them directly. Instead, the scanning tunneling microscope maps electronic structure. It reveals how electrons behave near the surface, and from that information, the arrangement of atoms can be resolved with astonishing precision. This made it possible not only to image surfaces, but also to interact with them in new ways. Scanning probe techniques, including methods related to the scanning tunneling microscope, have been used to move individual atoms on surfaces. One famous demonstration arranged atoms to spell out the letters of a company name, which is both a remarkable technical achievement and perhaps one of the most microscopic acts of branding in history. The deeper point is that scientists had gained a way to study and manipulate matter at a scale once beyond direct reach. The role of tunneling is central. Without the quantum ability of electrons to cross a tiny barrier between the tip and the sample, the scanning tunneling microscope would not work in the same way. The instrument depends on the fact that the barrier is narrow enough for the wave function to reach through it, and on the fact that the tunneling current changes so sharply with distance. The same effect that sounds like particles passing through walls becomes a measuring tool of breathtaking precision. This connects directly back to the strange question at the heart of tunneling. Can particles walk through walls? Not in the clumsy, everyday sense. Electrons do not stroll across the gap from tip to surface, and the barrier is not a brick wall politely letting them through. But their quantum wave functions can extend through a forbidden region, allowing a measurable probability of crossing. In the scanning tunneling microscope, that probability becomes information. The wall, in this case, becomes a way of seeing. The tiny forbidden gap between tip and surface is not merely an obstacle. It is the very thing that allows the instrument to sense the surface so finely. Quantum tunneling does not just explain how particles can cross barriers. It gives science a way to feel the shape of matter at the scale of atoms, quietly tracing the surface of reality one tunneling electron at a time. Some forms of tunneling involve a single particle facing a tiny barrier. An alpha particle escapes a nucleus. An electron crosses a thin insulating gap. A proton in the sun's core gets close enough for nuclear fusion to begin. But quantum tunneling can also appear in systems that feel larger and more organized, where many particles behave together in a carefully protected quantum state. One of the most important places this happens is superconductivity. Superconductivity is a state in which certain materials conduct electricity with no electrical resistance below a critical temperature. In an ordinary wire, electrons moving through the material lose energy as they scatter from atoms, vibrations, and imperfections. That resistance turns some electrical energy into heat. It is why electrical devices can warm up, and why power cables are not always thrilled about their responsibilities. A superconductor behaves differently. Below its critical temperature, electrical current can flow without ordinary resistance. This does not happen in every material, and it usually requires very low temperatures, though different superconductors have different critical temperatures. The effect was discovered in 1911 by Heike Kamerlingh-Onnes, who found that mercury lost its electrical resistance when cooled to extremely low temperatures. Even before tunneling entered the story, superconductivity already looked like one of nature's quieter acts of rebellion. For many years, superconductivity was difficult to explain. The eventual breakthrough came from John Bardeen, Leon Cooper, and John Robert Schrieffer, who developed the Bardeen-Cooper-Schrieffer theory in 1957. This theory explains conventional superconductivity by showing how electrons can form linked pairs called Cooper pairs. Normally, electrons repel each other because they carry the same negative electric charge. But inside certain cold materials, interactions with the crystal lattice allow electrons to become paired in a collective quantum state. That collective state is the essential point. In a superconductor, the current is not simply a crowd of independent electrons wandering through a material like slightly confused commuters. The paired electrons behave as part of one coherent quantum system. Coherence means that the quantum relationships across the system remain orderly enough for wave-like behavior to matter on a larger scale than usual. It is delicate, precise, and very unlike the messy electrical motion found in ordinary conductors. Then came Brian Josephson. In 1962, while still a graduate student, Josephson predicted that a superconducting current could tunnel through a very thin insulating barrier placed between two superconductors. This was a remarkable idea. An insulator, by ordinary expectation, should block electrical current. But if two superconductors were separated by an extremely thin barrier, the collective quantum state on one side could connect with the collective quantum state on the other. The result became known as the Josephson effect. A Josephson junction is the device built around this principle. It consists of two superconductors separated by a thin insulating layer. The barrier is real. The insulator matters. Yet under the right conditions, Cooper pairs can tunnel through it. This is not quite the same as a lone electron crossing a barrier. It is tunneling involving a macroscopic quantum state, meaning a quantum state that can extend across a structure large enough to be engineered, cooled, connected, and measured. That phrase can sound dangerously close to saying that big objects can now casually tunnel through walls, so it needs careful handling. A Josephson junction does not mean chairs. People or sleepy cats can pass through brickwork if they become sufficiently superconducting in spirit. The system works because it is carefully prepared, extremely small in the relevant region, and usually kept at very low temperatures. The coherence of the superconducting state is protected enough for quantum tunneling to appear in a measurable, controlled way. The Josephson junction became one of the most important tunneling devices in physics and technology. Because the tunneling current responds with extraordinary sensitivity to magnetic fields, Josephson junctions are used in superconducting quantum interference devices, which are among the most sensitive magnetic field detectors ever made. These instruments can measure incredibly tiny magnetic signals, useful in areas ranging from materials science to medical and biological research. Josephson junctions also play a role in voltage standards. The relationship between voltage and frequency in the Josephson effect is so precise that it has been used to define and reproduce electrical voltage with extraordinary accuracy. In this case, quantum tunneling is not just a strange crossing through a forbidden barrier. It becomes a ruler for measurement itself, a way of turning quantum behavior into a standard that laboratories can trust. They also appear in some approaches to quantum computing. Superconducting qubits, used by research groups and companies including IBM, Google, and academic laboratories around the world, often rely on circuits containing Josephson junctions. A qubit is a quantum system used to store and process quantum information. In superconducting circuits, Josephson junctions help create controllable quantum energy levels, making it possible to build artificial quantum systems that can be manipulated with microwave signals. This shows how far the idea of tunneling can travel. It begins as a puzzle about particles crossing barriers they should not cross. It helps explain radioactive decay and nuclear fusion. It allows electrons to move through thin barriers in materials. And in superconductors, it becomes part of a collective quantum phenomenon, where many particles behave together in a state delicate enough to reveal nature's deeper rules. The wall is still there. The insulating barrier in a Josephson junction is not imaginary. But in a carefully cooled and carefully engineered system, the quantum state does not treat that barrier as an absolute end. It reaches through, links the two superconductors, and allows current to flow in a way classical physics would never have expected. The impossible shortcut, once again, is not a fantasy. It is a controlled feature of reality, made visible when matter is arranged so gently and precisely that quantum coherence has room to breathe. The same tunneling that appears in nuclei, stars, and carefully built superconducting junctions also lives inside the devices scattered all around modern life. It is hidden in places too small to see, buried inside chips, memory cells, sensors, and electronic structures where the walls are not made of brick or stone, but of energy barriers only a few atoms thick. Modern electronics depends on controlling the motion of electrons through materials. That may sound simple, as if electrons are tiny beads being pushed through tiny pipes, but the real story is far more quantum. Inside a semiconductor, electrons occupy allowed energy states. They respond to electric fields, material boundaries, impurities, and the structure of the crystal. Their behavior is not just a matter of classical particles drifting around. It is shaped by wave functions, energy bands, and barriers that can sometimes be crossed by tunneling. The semiconductor revolution grew from the invention of the transistor. At Bell Labs, John Bardeen, Walter Brattain, and William Shockley helped develop the first transistor in the late 1940s, creating a device that could amplify signals or act as a switch. That discovery transformed electronics. It led toward radios, computers, satellites, phones, digital cameras, medical devices, and a world in which a person can carry more computing power in a pocket than earlier generations could fit inside whole rooms. This is both impressive and slightly unfair to anyone who once had to book time with a machine the size of furniture. A central device in modern digital electronics is the metal oxide semiconductor field effect transistor. The name sounds long enough to be a small technical obstacle in its own right, but the idea can be introduced gently. It is a transistor in which an electric field controls whether current can flow through a semiconductor channel. A metal or conducting gate sits above an insulating oxide layer, and changing the voltage at the gate changes the behavior of electrons in the channel below. In digital circuits, this allows the device to act like a switch, helping represent the on and off states used in computation. The insulating layer in these devices is meant to be a barrier. It helps separate the gate from the conducting channel, allowing control without direct current simply flowing straight through. But as transistors became smaller and smaller, that insulating layer had to become thinner. At larger scales, it behaved like a reliable wall. At extremely small scales, the wall became thin enough for electrons to notice in a very quantum way. When an insulating barrier is only a few atoms thick, electron tunneling can occur. The electron does not need to have enough classical energy to pass over the barrier. Its wave function can extend into the forbidden region, and if the barrier is thin enough, there can be a measurable probability of appearing on the other side. In some devices this is useful, in others it is a problem. Engineers may want an insulating layer to block current, but quantum tunneling can allow a small leakage current to slip through anyway. This leakage is one of the reasons nanoscale electronics is so difficult. Shrinking devices makes them faster, denser, and more efficient in many ways, but it also brings quantum effects closer to the surface. The smaller the structures become, the less the old classical picture can be taken for granted. Barriers that once seemed comfortably thick become almost transparent to some electrons. The walls inside chips are not always walls in the everyday sense. Sometimes they are thin regions of fading probability. Flash memory provides a useful example of tunneling being deliberately used rather than merely endured. Flash memory stores information by placing electric charge in tiny structures within a memory cell. In many designs, electrons are moved through an insulating barrier during writing or erasing. This can involve quantum tunneling or closely related high-field tunneling processes, allowing charge to be added or removed from a floating gate or charge trapping layer. The stored charge then changes the electrical behavior of the cell, letting the device remember information even when the power is switched off. That means tunneling is involved in the practical business of digital storage. Photos, documents, videos, applications, and settings can depend on tiny movements of charge through barriers that would look impossible from a classical point of view. The same principle behind the question of whether particles can cross walls becomes part of the reason a phone remembers a message, a camera stores an image, or a computer keeps data on a solid-state drive. This does not mean every part of modern electronics is simply tunneling in disguise. Most device behavior involves a rich mixture of semiconductor physics, electric fields, band structure, thermal effects, material engineering, and circuit design. Tunneling is one important piece, sometimes helpful, sometimes troublesome, and often unavoidable as structures approach atomic dimensions. The deeper lesson is that quantum mechanics is not confined to exotic laboratories. It is not only about strange particles in distant experiments, it sits quietly inside everyday technology. As electronics shrink, the old question of particles crossing barriers becomes a practical engineering concern. A wall that looks absolute to classical physics may become, at nanoscale distances, a region where probability reaches through. In that hidden landscape of silicon, oxide, charge, and carefully arranged atoms, quantum tunneling is no longer just an impossible shortcut. It is part of the machinery of the modern world. Quantum tunneling does not stop at nuclei, stars, microscopes, or electronics. It can also appear in chemistry, where atoms rearrange, bonds break, bonds form, and matter quietly changes its shape. At first, chemistry may seem like a softer, more familiar place than the solar core or a superconducting circuit. It belongs to liquids in flasks, reactions in cells, the scent of flowers, the browning of toast, and the mysterious ability of one forgotten cup of tea to become undrinkable with great confidence. But beneath those everyday changes, the same quantum rules still apply. A chemical reaction often has to overcome an energy barrier. This barrier is called activation energy. It is the energy needed to move the reacting molecules from their starting arrangement toward a transition state, where old bonds are partly broken and new bonds are partly forming. In a classical picture, the reacting particles must have enough energy to climb over this barrier. If they do not, the reaction does not proceed. The particles collide, shuffle, separate, and nothing much changes. Rather like guests at a party who have been introduced but immediately realize they have no chemistry at all. Quantum mechanics adds a more subtle possibility. In some reactions, especially those involving very light particles such as electrons or protons, tunneling can allow part of the quantum state to pass through the energy barrier rather than climb over it. This does not replace ordinary chemistry. Most chemical behavior still depends on molecular structure, temperature, electric charge, bond energies, solvents, and the shapes of reacting molecules. But tunneling can sometimes influence how quickly a reaction happens, especially when the barrier is narrow and the particle involved is light. Friedrich Hund was one of the physicists connected with early work on tunneling and molecular quantum mechanics. In the early development of quantum theory, physicists were beginning to understand that molecules could not be explained only by classical pictures of balls and springs. Electrons, nuclei, and bonds had to be described with quantum states. In that setting, tunneling became part of the explanation for how particles could move between arrangements that classical physics would treat as separated by an energy barrier. Proton tunneling is one important example. A proton is the nucleus of a hydrogen atom, and because it is far lighter than most atomic nuclei, its quantum behavior can be significant in certain molecular situations. In hydrogen transfer reactions, a proton may move from one part of a molecule to another, or from one molecule to another. Classically, it would need enough energy to cross the activation barrier. Quantum mechanically, if the barrier is narrow enough, there can be a probability that the proton tunnels through. This matters most at tiny scales and under specific conditions. It is not a universal shortcut that makes every reaction easy. The details depend on the shape of the energy barrier, the distance the proton must move, the surrounding molecular environment, and the temperature. Sometimes tunneling makes only a small correction. Sometimes it can make a reaction noticeably faster than a purely classical model would predict. The important point is not that chemistry becomes magical, but that chemistry becomes more accurate when the quantum nature of light particles is included. Enzymes provide a careful example. An enzyme is a biological catalyst, a molecule, usually a protein, that speeds up a chemical reaction without being consumed by it. Enzymes work mainly by binding reactants in useful positions, stabilizing transition states, shaping the local chemical environment, and lowering activation energy. In some enzyme reactions, proton tunneling or electron tunneling may contribute to the reaction rate, but it would be misleading to say that tunneling explains enzymes by itself. Enzymes are not little quantum wizards in folded protein robes. They are complex molecular machines, and tunneling is one possible physical ingredient within some of their reactions. Electron tunneling also appears in biology. In cellular respiration, electrons move through chains of proteins embedded in membranes, helping cells extract usable energy from food. In photosynthesis, electrons move through molecular structures after light is absorbed, helping convert solar energy into chemical energy. These electron movements occur over extremely small distances inside carefully arranged protein environments. Because electrons are light quantum particles, tunneling can be part of how they move between molecular sites. This does not mean biology is secretly mystical. It does not mean tunneling explains consciousness, life force, intention, or any of the grand claims that sometimes gather around the word quantum, like fog around a street lamp. The real science is more restrained and more interesting. Quantum tunneling can affect specific processes involving electrons and protons in molecules. It can influence reaction rates, charge transfer, and the fine details of biological chemistry. But it remains a precise physical effect, not a blank check for mystery. The same pattern keeps appearing. A barrier exists. Classical physics says a particle should need enough energy to climb over it. Quantum mechanics says the wave function may extend through it. If the barrier is narrow enough and the particle is light enough, the probability can matter. In chemistry and biology, these barriers are not walls of stone, but energy landscapes shaped by bonds, charges, molecular geometry, and the surrounding environment. So the question of particles walking through walls becomes quieter here, but not less remarkable. Inside molecules, the wall may be an activation energy barrier. The particle may be an electron or a proton. The shortcut may change the speed of a reaction, or help charge a move through a protein. It is not dramatic in the theatrical sense. There is no tiny proton kicking down a molecular door. But there is a real quantum possibility reaching through a barrier that classical chemistry alone would not fully explain. In this way, tunneling enters the chemistry of matter and the chemistry of life. Not as magic, not as a universal answer, but as one more sign that the microscopic world is governed by rules both delicate and exact. Even in the soft machinery of living cells, reality sometimes works by allowing possibility to pass through what once looked closed. The phrase particles walking through walls is useful, because it gives the mind something solid to picture. It takes a strange quantum process and turns it into a familiar image, a thing, a wall, and the surprising possibility of ending up on the other side. But the moment that image is brought up to human size, the answer becomes reassuringly firm. No, people cannot tunnel through walls in any meaningful practical sense. This is not because quantum mechanics suddenly stops applying to people. Human bodies are made of atoms, and atoms are quantum objects. The issue is scale, complexity, and probability. A single electron near a barrier only a few atoms thick is one thing. A person facing a brick wall is something else entirely. A person is made of an enormous number of atoms, arranged into molecules, cells, tissues, organs, bones, blood, and all the other ingredients required for being inconveniently solid. Those atoms are not isolated. They are constantly interacting with one another and with the surrounding world. A human body is warm. It vibrates internally. It exchanges heat with the air. It absorbs and emits radiation. It is struck by light. It pushes against the floor. It breathes, shifts, settles, and remains connected to its environment in countless microscopic ways. Even sitting perfectly still, the body is not a quiet quantum object floating in pristine isolation. It is a busy, noisy, thermally active system, which is a polite scientific way of saying that the universe is constantly poking it. This matters because delicate quantum behavior is easily disrupted. The relevant idea is decoherence. Decoherence is the process by which interactions with the environment cause a quantum system to lose the clear relationships needed for superposition and interference to remain observable. In a carefully controlled experiment, a tiny particle can sometimes maintain quantum behavior long enough for wave-like effects to be measured. But a large, warm, complicated object interacts with its surroundings so intensely that those delicate quantum possibilities are effectively washed out almost immediately. Wojciech Zurek has been one of the important figures in developing the modern understanding of decoherence, including ideas connected with quantum Darwinism. Quantum Darwinism is a way of thinking about how the environment effectively selects and spreads certain stable information about a quantum system, making the world appear classical at large scales. In simpler terms, the reason a chair looks like it is in one place, rather than a delicate blur of many possibilities, is partly because the chair is constantly interacting with its environment. The environment records where it is. Light scatters from it. Air molecules bounce from it. Heat moves through it. The chair does not get much privacy. The same is true of a person, only with even more internal activity. For a person to tunnel through a wall, it would not be enough for one electron or one proton to do something quantum and unusual. The entire arrangement of the person would have to appear on the other side in the correct form. All the atoms would have to participate coherently enough for the body to cross the barrier as a whole, while still remaining a person rather than a deeply unfortunate cloud of misplaced chemistry. The wall, meanwhile, is also made of atoms, with its own vibrations, bonds, thermal motion, and environmental interactions. The probability of that happening is not just small, it is so fantastically small that ordinary words like unlikely begin to feel embarrassed. It is not like winning a lottery. It is not like being struck by lightning on the same day that a meteor politely lands in the garden. Those are rare events, but they still belong to the realm of things that can happen in the ordinary world. A person tunneling through a wall would require a coherent quantum event involving an enormous number of particles across a barrier vastly wider than the atomic barriers where tunneling matters. On any meaningful human timescale, the probability is effectively zero. This is where quantum mechanics is often misunderstood. It does not say anything is possible in the loose, dreamy sense. It does not turn the universe into a place where every imaginable event has a friendly little chance of occurring if one waits with enough optimism and snacks. Quantum theory gives specific probabilities. Some of those probabilities are large enough to measure. Some are tiny but still important, as in alpha decay or fusion in the sun. Others are so small that nature might as well have nailed the door shut, bricked it over, and placed a very calm sign on it, reading no. Individual particles can tunnel because their quantum states can remain relevant across tiny barriers. An electron approaching an insulating layer only a few atoms thick may have a wave function that extends far enough through the barrier for tunneling to occur. An alpha particle inside a nucleus may have a small probability of escaping. A proton in the Sun may occasionally get close enough to another proton for fusion to proceed. These are small systems, small distances, and specific energy barriers. A person and a wall are not that kind of system. They are macroscopic, messy, warm, entangled with the environment, and enormously complex. The quantum rules are still underneath everything, but their weirdest possibilities are buried under scale, interaction, and probability. The classical world emerges because for large objects the quantum alternatives become so suppressed that only the ordinary outcome remains visible. So the wall stays a wall, the person stays on one side of it. Quantum tunneling is real, but it is not an escape plan for the human body. It is a precise microscopic process, not a loophole for walking through architecture. At some point, the question becomes not only how tunneling happens, but what it means to say that it happens at all. A particle approaches a barrier. Later it is detected on one side or the other. Sometimes it is reflected back. Sometimes it appears beyond the barrier. The mathematics gives probabilities for these outcomes with remarkable success. But the picture in the mind can still feel incomplete, because tunneling does not look like an ordinary journey. In everyday life, motion usually comes with a path. A person crosses a room by passing through the space between one side and the other. A car goes through a tunnel by entering at one end, travelling along the road and leaving at the far end. Even a thrown stone, if filmed carefully enough, can be traced from hand to landing place. Classical motion is comfortable because it feels continuous. Something is here, then somewhere nearby again, until it arrives there. Quantum tunneling resists that simple picture. Before measurement, quantum theory describes the particle through a wave function. That wave function contains the possible outcomes of the situation. In the tunneling problem, those possible outcomes include reflection from the barrier and transmission through the barrier. Reflection means the particle is found back on the original side. Transmission means it is found beyond the barrier. The theory does not usually describe the particle as a tiny bead secretly taking a hidden route through the wall in the ordinary classical sense. Instead, the quantum state evolves according to the rules of quantum mechanics. The wave function reaches the barrier, changes its behavior inside the classically forbidden region, and may have a small but non-zero presence on the far side. When a measurement is made, the particle is found in one outcome or another. The important point is that standard quantum mechanics does not need to imagine the particle travelling through the barrier like a miniature burglar in a very narrow corridor. It describes the wave function, the barrier, and the probabilities of what can later be observed. This is where interpretation enters. The Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg, treats the wave function as a tool for predicting measurement outcomes. In this view, quantum mechanics tells us what can be said about the results of experiments, and it warns against assuming that particles possess all ordinary classical properties before those properties are measured. The exact philosophical details are debated, but the practical lesson is clear enough. The quantum world cannot always be translated into a simple story of little objects following hidden everyday paths. Other interpretations describe the situation differently. Hugh Everett's many worlds interpretation treats all possible outcomes as part of a larger branching quantum reality, so transmission and reflection are not reduced to a single classical-looking story in quite the same way. David Bohm's pilot wave theory offers another picture, where particles do have definite positions guided by a deeper wave structure. These interpretations disagree about what the wave function ultimately represents, but they all have to account for the same experimental facts. Tunneling is measured. The probabilities are real. The barrier is crossed often enough for the effect to shape nuclear decay, sunlight, electronics, microscopes, and superconducting devices. This is a useful place to be careful. Quantum tunneling does not prove that reality is an illusion. It does not show that consciousness creates matter. It does not mean particles make decisions, notice walls, or decide to be awkward because the universe enjoys confusing physics students at low-light levels. The scientific claim is more precise and more restrained. A quantum system is described by a wave function. That wave function can extend into regions where classical motion would be forbidden. Measurement reveals outcomes with probabilities predicted by the theory. The mystery is not that physics has become lawless. It is almost the opposite. Tunneling is strange because the rules are so exact. The mathematics can predict how the probability changes when the barrier becomes wider, higher, thinner, or lower. It can explain why alpha particles escape nuclei at particular rates, why electrons cross tiny insulating gaps, and why certain devices work at all. If tunneling were merely a vague miracle, it would not be so useful. Its power comes from being both deeply unintuitive and reliably calculable. The reason it feels impossible is that human intuition was not built around wave functions crossing nanometer scale barriers. It was built around hands, stones, doors, hills, fires, tools, and large objects that remain reassuringly where they appear to be. A nanometer is 1/1000th of a meter, a scale far below ordinary sensation. At that scale, the old image of a particle as a tiny hard object with a neat little path begins to fail. The particle is still real, and the barrier is still real, but the relationship between them is governed by quantum probability rather than ordinary motion. So what actually happens when a particle tunnels? The most honest answer is that the quantum state evolves across the barrier, and measurement may reveal the particle on the far side. That may not satisfy the part of the mind that wants a tiny cinematic journey through the wall, but it is the answer that experiments support. The particle does not walk. The wall does not vanish. Reality does not lose interest in its own rules. Instead, the rules are simply deeper than the ones large objects taught the mind to expect. Tunneling is not a secret passage hidden inside the barrier. It is the measured consequence of a wave function, reaching where classical motion says it should not go, and occasionally leaving a particle there when nature is asked what happened. So, can particles walk through walls? The clearest answer is no, not in the way the phrase first suggests. A particle does not become a tiny person, lean forward with quiet confidence, and stroll through a wall as if the rules of matter have briefly looked the other way. But in the precise language of quantum mechanics, a particle can pass through an energy barrier that classical physics says it should not be able to cross. That is quantum tunneling. Not walking, not ghosting, not cheating, but a real and measurable form of transmission through a classically forbidden region. The journey begins with the older picture of barriers. In classical physics, an object either has enough energy to cross an obstacle, or it does not. A ball rolls over a hill if it has enough kinetic energy. If it lacks that energy, it rolls back. A locked door remains locked unless something opens it, breaks it, or reveals that the builder had a very relaxed relationship with door frames. This view works beautifully for ordinary objects, and it remains one of the reasons the world feels solid, predictable, and safe enough to walk around without expecting the furniture to blur through the floor. Then matter began to reveal a deeper nature. Light behaved like both a wave and a stream of packets. Energy appeared in discrete amounts. Electrons occupied quantist energy levels rather than any orbit they pleased. Louis de Broglie proposed that matter itself had wave-like properties, and experiments by Clinton Davison and Lester Germer showed that electrons could diffract like waves. This did not mean electrons were tiny ripples of water. It meant their behaviour could not be fully captured by the image of little solid balls travelling along neat invisible tracks. The wave function became the key idea. Erwin Schrödinger's equation gave physicists a way to describe how quantum states change over time, while Max Born's probability interpretation showed that the wave function is connected to the likelihood of measurement outcomes. A particle, before measurement, is not described in standard quantum mechanics as having one fully classical root waiting to be revealed. It is described by a quantum state, and that state can spread, interfere, fade, and sometimes reach beyond places classical physics would forbid. That is where the barrier changes meaning. A quantum barrier is often not a physical wall made from bricks, but an energy barrier created by electric forces, nuclear forces, or material boundaries. In a classically forbidden region, the particle has less energy than the potential energy associated with that region. Classical mechanics says the particle should not be there. Quantum mechanics says the wave function may enter that region and decay rather than vanish instantly. If the barrier is thin enough, some part of that wave function may still reach the far side, leaving a real probability of detecting the particle beyond it. This is not a loophole in physics, it is physics. The same principle explains alpha decay, where an alpha particle can escape an atomic nucleus despite being trapped behind a nuclear energy barrier. George Gamow, and independently Ronald Gurney and Edward Condon, showed how tunneling could explain why unstable nuclei decay at measurable rates. The alpha particle does not climb over the barrier. Its wave function allows a small probability of being found outside, and over many atoms those probabilities become the predictable pattern of radioactive half-life. The same idea also helps the sun shine. In the sun's core, protons repel one another because they carry positive electric charge. The core is immensely hot, around 15 million degrees Celsius, but temperature alone does not fully solve the problem. Quantum tunneling allows some protons to get close enough for the strong nuclear force to bind them, helping nuclear fusion proceed. Arthur Eddington saw that stars could be powered by nuclear processes, and Hans Bethe later explained stellar fusion in detail. The light arriving quietly on Earth carries, hidden inside its long history, the work of quantum probability deep in a star. In electronics, tunneling becomes something that can be engineered. Electrons in solids are governed by energy bands, crystal structures, and quantum states, not tiny classical orbits. Felix Bloch helped build the quantum theory of electrons in crystals. Leo Isaki's tunnel diode showed that tunneling through a thin semiconductor junction could become a useful device. The scanning tunneling microscope, developed by Gerd Binnig and Heinrich Rohrer at the International Business Machines Research Laboratory in Zurich, turned tunneling into a way of mapping surfaces with atomic precision. Josephson junctions, predicted by Brian Josephson, showed that superconducting current could tunnel through a thin insulating barrier between superconductors, linking the effect to sensitive magnetic field detectors, voltage standards, and some superconducting quantum computers. Tunneling even appears in chemistry and biology, where light particles such as electrons and protons can sometimes pass through activation energy barriers. It may influence certain hydrogen transfer reactions, enzyme processes, respiration, and photosynthesis. But this must be kept precise. It does not explain consciousness, life force, intention, or any misty idea wearing a borrowed lab coat. It is a real physical effect with real but limited relevance in specific molecular conditions. Ordinary walls, meanwhile, remain safe from casual human tunneling, which is good news for privacy, architecture, and anyone keeping biscuits hidden in a cupboard. A person is made of an enormous number of atoms, constantly interacting with one another, with heat, air, light, and the surrounding environment. Decoherence, a concept strongly associated with Wojciech Zurek, explains why delicate quantum possibilities become effectively suppressed in large, warm, complex systems. For a whole person to tunnel through a wall, an absurd number of particles would need to behave coherently across a huge barrier. The probability is so small that, for any meaningful purpose, nature might as well have sealed the wall twice and then leaned on it. That is the quiet strangeness of tunneling. Reality is reliable at human scales, yet deeply non-classical at microscopic scales. Matter is not less real because quantum physics describes it. It is more subtle than it first appears. The universe does not always forbid an outcome simply because classical intuition cannot imagine the path. Sometimes, at the smallest scales, the wall remains real, the barrier remains difficult, and yet probability reaches just far enough for the impossible shortcut to become ordinary physics. So, can particles walk through walls? The calm answer is that particles can pass through barriers by quantum tunneling, but they do not walk through walls in the ordinary human sense. They do not stroll, choose, sneak, or drift through solid matter like tiny ghosts with excellent timing. What happens is stranger, quieter, and more precise. A quantum particle is described by a wave function, and that wave function can extend into a region that classical physics says the particle should not be able to enter. In classical physics, a barrier is usually absolute. If an object does not have enough energy to cross it, it stops or turns back. But in quantum mechanics, a barrier is not always the final edge of possibility. Inside a classically forbidden region, the wave function can decay rather than vanish instantly. If the barrier is thin enough and not too high in energy, a small part of that wave function may still reach the far side. That gives the particle a real probability of being detected beyond the obstacle. This probability is not vague guesswork. It depends on the height and width of the barrier, and it usually falls extremely quickly as either one increases. That is why tunneling can matter for electrons, protons, and alpha particles crossing tiny energy barriers, while remaining effectively impossible for people, chairs, cats, or anyone attempting to avoid opening a door properly. Across this journey, tunneling has appeared in many forms. It helps explain alpha decay, where particles escape unstable atomic nuclei. It helps the sun shine, allowing some protons in the solar core to get close enough for nuclear fusion. It appears in electron tunneling, tunnel diodes, scanning tunneling microscopes, Josephson junctions, modern electronics, flash memory, and carefully selected chemical and biological reactions involving protons or electrons. But the boundary matters. Quantum tunneling is real, measurable, and technologically useful. It does not mean ordinary objects can realistically pass through walls, and it does not mean quantum physics allows anything imaginable to happen. Quantum mechanics gives specific probabilities, and many of those probabilities are so tiny that the ordinary world remains solid, stable, and reassuringly inconvenient. Quantum tunneling is not a breakdown of reality. It is one of reality's operating rules at small scales. The impossible shortcut is only impossible from the classical point of view. Beneath ordinary matter, the universe is governed by rules stranger than everyday experience suggests, but also more precise, more subtle, and more beautifully exact than common sense alone could ever have guessed.